Hello everyone, welcome to my talk. I'm Zhenpeng Chen from UCL. It's my great honor to have this opportunity to introduce our FSC work. MAAT, a novel ensemble approach to addressing fairness and performance bugs for machine learning software. This is the joint work with Dr. Zhang from KCL, and Professor Federica Sarro and Professor Mark Harman from UCL. Fairness is important for machine learning software. In the machine learning community, there is growing interest in fairness. In the software engineering community, it is also widely acknowledged that software fairness is analogous to software quality and needs to be the first-class entity in the software engineering process. Researchers have also defined a new kind of software bug named fairness bug, which refers to the imperfection in software that causes its unfair behaviors. The literature has witnessed increasing results on detecting and addressing fairness bugs. Let's start with background knowledge. Machine learning software needs to protect some human attributes against unfairness, such as sex, race, and so on. Based on a protected attribute, a population is divided into privileged and unprivileged groups. Compared to privileged group, members in the unprivileged group are often at a disadvantage. For example, in the hiring process, the male group is often privileged, while the female group is unprivileged. Group fairness requires privileged and unprivileged groups are treated equally by machine learning software. For example, having an equal acceptance rate or predictive performance. To address fairness bugs and achieve group fairness, researchers have proposed various bias mitigation methods. These methods have the same goal, that is fairness improvement. Recently, researchers have also proposed ensemble techniques that combine different bias mitigation methods to further improve fairness. However, fairness improvement comes at a price. The reduction of fairness bugs often comes at the cost of introducing more performance bugs, causing decrease in machine learning performance, such as accuracy decrease. This is widely known as fairness performance trade-off. To improve such trade-off, we propose MAAT, a fairness performance ensemble approach. Different from conventional ensemble methods that combine models guided with the same objective, MAAT combines two models optimized for different objectives. We train two individual models named the fairness model and the performance model. The fairness model is optimized for fairness, while the performance model is optimized for machine learning performance. Each model maps the input to a probability vector, indicating the probability that the input belongs to the favorable or unfavorable class. We then combine the output probability vectors of the fairness model and the performance model to produce the final prediction. We first look at the performance model. By default, the machine learning training process uses machine learning performance as the optimization goal. So we use the machine learning models obtained by traditional machine learning algorithms on the original training data as the performance model. Then, how to obtain the fairness model? As the Turing Award winner Ian LeCun said, algorithms trained on biased data are biased. That means training data bias is the root cause of machine learning software bias. For example, in the adult dataset, which is commonly used for income prediction, 31% of men are labeled with high income and 11% of women, a difference of almost 3 times. Therefore, machine learning software developed on this dataset tends to favor men. Thus, to mitigate machine learning software bias, we use data debugging to mitigate bias in training data. Specifically, we debug the training data by encoding the "we are all equal" worldview into it. This worldview holds the belief that there is no statistical association between outcome decision and protected attribute. To encode the worldview, we first divide the training data into 4 subgroups based on outcome label and protected attribute. Then, we need to make the favorable rates of privileged and unprivileged groups equal to satisfy the "we are all equal" worldview. How to make the rates equal? Since many studies have shown that Machine learning software tends to falsely produce the favorable label for the privileged group members and the unfavorable label for the unprivileged. Training data bias mainly exists in the privileged favorable subgroup and unprivileged unfavorable subgroup. Therefore, we reduce data samples in the two subgroups to alleviate data bias and make the favorable rates equal between the privileged and unprivileged groups. Meanwhile, we keep the ratio of privileged and unprivileged individuals equal to that of the real world. Based on the constraints, we calculate the numbers of samples that need to be reduced and randomly remove these samples from the two subgroups. Based on the remaining data, we train the fairness model to predict favorable or unfavorable outcome. Now we have the performance model and the fairness model. How to combine them? Let's consider a binary classification task. Both models can predict the probabilities that the input belongs to the favorable or unfavorable class respectively. Then we average the two probability vectors to obtain the final probability vector. If the averaged probability of the unfavorable class is greater than that of the favorable, we predict the input as unfavorable, otherwise favorable. To evaluate MAAT, we use 7 widely adopted datasets. We also choose 5 state-of-the-art bias mitigation methods for comparison. We evaluate MAAT and these methods in terms of 15 fairness performance measurements. That is combinations of 3 fairness metrics and 5 machine learning performance metrics. We implement each bias mitigation method using 3 popular machine learning algorithms. We adopt the state-of-the-art benchmarking tool, namely Failure, to evaluate the fairness performance trade-off. Failure provides a unified trade-off baseline to evaluate and compare different bias mitigation methods. We evaluate MAAT by answering 4 research questions. First, what fairness performance trade-off does MAAT achieve according to Failure? Second, how well does MAAT apply to different scenarios? Third, how do different fairness models and performance models affect MAAT? The last question is, how do different combination strategies affect MAAT? The first question evaluates the effectiveness of MAAT and existing methods in fairness performance trade-off. In each of the 7 tasks, each method is applied with 3 machine learning algorithms 50 times. We treat each single run as an individual case. We compare MAAT and existing methods in terms of the unified baseline provided by Failure, and calculate the proportion of cases beating the baseline for each method. We find that MAAT beats the baseline in 92% of the overall cases evaluated, 12 percentage points more than the best technique currently available. To evaluate the applicability of MAAT, we compare MAAT with existing methods on different scenarios. From the figure, we can observe that MAAT beats the unified baseline in more cases than existing bias mitigation methods on each machine learning algorithm, each decision task, and each fairness performance measurement we studied. Then we explore the influence of fairness model on MAAT. We replaced our training data debugging technique with the existing bias mitigation methods, as these methods can also improve fairness. We choose 3 existing methods that can produce the probability vector that MAAT requires. We calculate the proportions of cases beating the baseline constructed by Failure, and find that when applied under the framework of MAAT, the fairness performance trade-off of these existing bias mitigation methods is all improved. Nevertheless, our training data debugging technique is still more effective than existing methods. What about the influence of performance model? We use different machine learning algorithms to obtain different performance models, while keeping the fairness model unchangeable. We show the accuracy of these performance models and the corresponding fairness performance trade-off results of them in the figure. As shown, MAAT tends to have better effectiveness with more accurate performance models. The last research question explores the influence of combination strategies. We combine the output probability vectors of the performance model and the fairness model in different proportions. We present the result for each strategy in each task and over all tasks, and find different tasks have different optimal combination strategies. Overall, the averaging strategy that we adopt by default achieves the best effectiveness. Finally, just to summarize this work, we propose the first ensemble approach that combines different machine learning properties. In this paper, we consider two important properties: machine learning performance and fairness. We propose MAAT to combine models with fairness and performance as objectives to improve fairness-performance trade-off for machine learning software. An extensive evaluation shows that MAAT achieves the state-of-the-art fairness-performance trade-off compared to existing bias mitigation methods. It is widely applicable to different scenarios. Our successful practice may also shed light on other trade-off problems in software development. You can find more details in our paper if you are interested. Thanks for your attention.